The topic is three tests for convergence and divergence. And if you're following along in the Thomas textbook, this is sections 10.3 and 10.4. The three tests that we're going to cover are the integral test, the direct comparison test, and the limit comparison test. Now, I would imagine that these last two may sound a little bit familiar to you from the section on improper integrals. If so, I have some good news. They're basically the same test. They work very, very similarly to what we already saw in improper integrals. They just work for series as well. It's really the integral test that's going to be new, but we'll do some examples of all of them. So let me get to the definition of the integral test. So here's the integral test. The integral test is suppose that we have a sequence an, and it's equal to some function f. It's equal to some function f for all integer values greater than or equal to 1. And as we'll see, we don't really have to start at 1. We can start actually at anything, but just easier to state the test if we assume the sequence starts at 1. So now if f, this is the function by the way, this is a statement we're making about the function f, not the sequence. If f is a positive, continuous, and decreasing function, then in order to determine whether this series converges, we can simply evaluate the improper integral of f. If the improper integral converges, then so does the series. If the improper integral diverges, then so does the series. So basically what this says is just take the series definition, just replace n with x to make it a function, and integrate the function on the interval 1 to infinity. And then the series behaves the same as the function does. If the integral of the series converges, if the integral of the function converges, then the series converges. If the integral of the function diverges, then the series diverges. The main issue here is that the function has to meet three different properties in order for this to be true. The function has to be positive. In other words, it should be greater than or equal to 0. Because technically 0 is not positive, but we'll include that. It has to be continuous, and it also has to be decreasing. So, and I've also noted here that, as I mentioned earlier, technically we don't really have to start at 1. It would be fine if we started, say, at 25 or 100 or a million or 100 billion. It doesn't matter because, as I've made this point before, we don't really care what happens. When we're integrating on the interval from 1 to infinity, we don't really care what happens to the first 100 billion terms. Because that's just going to come out to some finite number anyway. So it's like if it takes until, let's say, 25 before we get this nice convergence property that I'm trying to depict here, that's fine. We can use a different number. Okay, so let's do this example. So let's let S be this series, the series n equals 2 to infinity. The sum from n equals 2 to infinity of 1 over n times ln n. Let's determine whether this series converges or diverges. So first of all, let's note that an is just equal to 1 over n times ln n. So that's the definition of this of the underlying sequence, and this is valid for n greater than or equal to 2, since that's where we're starting. And we're going to define f of x. Actually, we don't have an f of x, so let's say let f of x equal 1 over x times ln x. So let's perform the integral test. And as I've said in the past, when you're performing a test, such as the ones we learned before, like the nth term test, you should really state the name of the test before you perform it, just so it's clear what mathematical theorem you're relying on to prove convergence or divergence. So first, let's observe that an, that's an a, is equal to f of n for all, I'll use the mathematical symbol for all the upside down a, n greater than or equal to 2. Now we have to verify that the three conditions are met. Recall that it was positive, continuous, and decreasing. So how do we show that? And we have to show that, by the way, about f, not a. In fact, it wouldn't even really make sense to say that an is, at least based on what we know about continuity so far, continuity is something that, as far as you've learned at this point, applies to functions that are defined on intervals of real numbers, not sequences defined on integers. So anyway, let's first verify that fn is positive. So is f of x positive for n greater than or equal to 2? The answer is yes. How do we know? Because we know that x is greater than 0 for all, sorry, I should have said for x greater than or equal to 2. X is greater than 0 for all x greater than or equal to 2. That's definitely true, since if x is at least 2, it's certainly at least 0. The next thing to note is that ln of x is also greater than 0 for all x greater than or equal to 2. How do we know that? We know that ln1 is equal to 0, and the ln function looks like this. Once it crosses the x-axis at 1, it just keeps going. It keeps going up and up and up, and it's always positive. It's just a feature that we know of that we know about the natural log function. So it's certainly the case that this denominator here, x times ln x, is going to be positive for all x greater than or equal to 2. So that's probably enough to say on that. Now we can ask, is f continuous for x greater than or equal to 2? The answer is yes. We know this. I'm not going to write out the explanation, but we know how to combine functions, how to combine continuous functions to produce a continuous function. This was something we all learned in Calc 1. That we learned that if I have two continuous functions and I multiply them, the result is also continuous. If I have two continuous functions and I divide one by the other, the result is always continuous as long as the denominator is not 0. So in this case, since we know that the denominator here is actually a positive continuous function, if I take 1 and divide it by another, 1 is a continuous constant function, I take it and divide it by this continuous function on the bottom, I get another continuous function. So you can reason that out however you want. We're not going to ask you to go through all the theorems from Calc 1 on continuity. It's just enough really to observe. As long as there's no serious doubt about the continuity of the function, it's enough just to observe that it's basically the sum, difference, product, or quotient of other continuous functions. So 3, I want to ask, is f decreasing? This is probably the one that involves the most work, especially the most work using calculus. Hopefully you recall how you prove that a function is increasing or decreasing from Calculus 1. The answer is you use a theorem called the monotone function theorem. And basically what the monotone function theorem says, you're going to say, wait, I never heard of the monotone function theorem. As soon as I say what it says, you're going to remember it. It says that if f prime is less than 0, then f is decreasing. And if f prime is greater than 0, then f is increasing. This concept is often, to Calc 1 students, becomes considered so synonymous with the idea of increasing and decreasing that they assume this is actually the definition of an increasing or decreasing function. It's not. This is a theorem about how to determine whether a function is increasing or decreasing. There's an algebraic definition of a function being increasing or decreasing, but this theorem from Calc 1 allows you to simply find the derivative of the function and just say the function is increasing or decreasing depending on whether its derivative is positive or negative. So all we have to do is calculate the derivative of f, and we can see if it is in fact less than 0 on the interval from 2 to infinity. So recall that f of x equals 1 over x ln x. So that means that f prime of x is equal to, using the quotient rule, it's going to be x ln x times the derivative of 1, which is 0, minus 1 times the derivative of the denominator, which we get through the product rule. That's going to be x times 1 over x plus the derivative of x is 1 times ln x, and take that all over x ln x squared. So let's see, so simplify this a bit, and this is equal to, since this term simply disappears because it's multiplied by 0, we just get negative x times 1 over x is 1, and then plus ln x over x ln x squared. So we can easily see that this is less than 0 for all x greater than or equal to 2. How do we know? The denominator is the square of something, so it's certainly positive. The numerator, in parentheses we have 1, we've already determined that ln x is a positive number for x greater than or equal to 2. So we're taking 1 plus ln x, which is positive, and we're flipping it around to negative. So we have a negative numerator over a positive denominator. Clearly we have a negative number. So we have in fact shown that the derivative is negative for the entire interval x greater than or equal to 2. So that means that f is decreasing. So now that we've verified that f actually meets all three conditions, we simply integrate f on the interval 2 to infinity. We simply calculate that integral. So this is equal to the integral from 2 to infinity of dx over x ln x. We know by definition that's equal to the limit as b approaches infinity of the integral from 2 to b of dx over x times ln x. And using u substitution, let's let u equal ln x, so du equals dx over x. That means that the given integral is equal to L limit. It's not three dots, just means that I'm continuing this equals here. So this is going to be the limit as b approaches infinity of the integral of du over u. I've got to change the limits. Since u equals ln x, that's going to be ln 2 up to ln b. And I can now, since ln b, I'm just going to show you a trick because I don't actually have to finish this problem, and I'll show you why. Since ln b grows to infinity, that means that this limit is actually equal to, I can just interchange this limit is actually, it can actually just be rewritten as ln 2 to infinity of du over u. Now why would I want to do that? The answer is because this is a, oops, I wanted to highlight it in red, this is a p integral. Remember, I don't actually have to evaluate the integral, I just have to say whether the integral converges or diverges. This integral, although the variable is u instead of x, this is a p integral with p is equal to 1, which is less than or equal to 1. So the answer is this diverges. So since the integral diverges, therefore we can conclude that the underlying series that was given, n equals 2 to infinity of 1 over n times ln of n also diverges. And that's the end of the proof. So we write a Halmos mark or a tombstone, and that's it. I usually like to show the whole problem so you can look at the whole thing, but unfortunately this is so long I don't think that it will fit reasonably on the page. So this is the problem that we did, and we use the integral test to show that that series diverges. You can move the tape back and, not the tape, the recording back and forth to see anything you want to see there.